Okay, Calc kids, this is section 2.5. Um, there's a few slides from the PowerPoint presentation that I want to go over first before we get into your homework, because I want you to understand the concept of continuity. That's kind of the topic of this section 2.5. Notice he kind of skipped section 2.4. Anyway, so I'm not going to go over every slide, so I'm not going to put it in presentation mode. I'm just going to hit the high points. This first definition here of continuous, this one, biggie. A function f is continuous at a number a if the limit of f of x as x approaches a equals the value of the function at point A. Now, remember when we first talked about limits? We talked about the fact that you could have the limit of some function equal a value, but that is not necessarily what the function equals at that value. So we have to be careful here. What this means is that the value of the function at a has to also equal the limit as x approaches a. So that's a biggie. The next slide is also important. Oh, I forgot I need to erase. So these three things are essentially what's implied from the definition we just talked about. So these are the three things that have to be true in order for a function to be continuous. And you might think that's not a big deal, but in calculus, what we can do with continuous functions versus other functions, it's a big deal. So three things that have to be true. F of a is defined. Okay, that is, a is in the domain of f. The limit of f of x as x approaches a exists, and obviously this was essentially the definition on the previous slide. The limit of f of x as x approaches a equals f of a. Okay, so again, what they're saying is if I have a graph and I have some function, I can't have like a dot here. If this is my a, I can't have a dot here that it's not defined. Like say down here was what my value of my function actually equaled, and this was an open dot. Can't have that. Okay, the value of the function at a point has to be the same thing as the limit as x approaches that point. Okay, so those are three important pieces that you need to understand for continuity. Now I'm going to jump down to slide, nope, next one, slide 7. Because I like the picture here better than the sad picture I just kind of drew. So figure 2 shows the graph of a function f. At which numbers is f discontinuous and why? Now, I don't know if you guys can see this, but this I think is an open circle. This is filled in. This is open. This is open. This is filled in, I think. Kind of hard for me to see as well. So it looks like there is a discontinuity when a equals 1 because the graph has a break there. Again, there's an open circle. Okay, so the value of the function f of 1 does not exist. Okay, it's an open circle. So is it continuous at that point? No. Now, what about 3? Is f continuous at 3? No, because actually the limit as x approaches 3. So the limit of f of x as x approaches 3 also does not exist. Why? Because from the left, it's going down to like a -1. And from the right, if we're going from the left, it's going down here negative. From the right, as we approach 3, it's up here at like 2 or 3 or 4 or whatever that would be, positive. So the limit of f of x as x approaches 3 doesn't even exist. So it's not continuous at that point. Now, at the point 5, is it continuous? Again, that's a no. Because, let me see if I can erase. Yeah, that's all right. Because although the limit of f of x as x approaches 5, it does exist, whatever that is. Let's say it's a 1. I don't know. Let's say that's 1. So the limit of f of x as x approaches 5 is 1 because it equals that from the left and the right. But that does not equal f of 5 does not equal 1. Okay, so again, another point of discontinuity. So in other words, when you're looking at a graph, anytime you would have to pick up your pencil, the function's not continuous at that point. Okay, so anytime if you're tracing the graph of a function and you'd have to pick up your pencil, it's not going to be continuous at that point. So again, the limit at a point has to exist and has to equal the value of the function at that point. Okay, hope that was helpful. There are a couple other things I want to hit on from the slides. What number is that? Nope. 11. The next one I want is 15. Give me just a minute. Now it's not sliding for me. One more. Okay. So here's some more definitions. A function f is continuous from the right at a number a if the limit as x approaches a, again, I want to point out that plus sign of f of x equals x of a, and it's continuous from the left. So let me say continuous from the right, and again, that's that plus sign. If the limit equals the value of the function at that point, and it's continuous from the left, again, notice the minus here, if the limit from the left equals the value of the function at that point. Okay, so we can also say continuous from the right, continuous from the left, if we're given a certain value. Instead of saying the entire function is continuous, we may have to break it up into pieces and just say, well, the whole thing's not continuous at a, but it's continuous from the left at a. So a function is continuous on an interval if it is continuous at every number in the interval. Okay, and that makes sense. So again, kind of goes hand in hand with the definition up above, which just says if the whole function isn't continuous, we can probably break up the domain into different intervals so that we can say, well, this interval is continuous and work with that. Okay, that's kind of where that's going. Okay, let me scroll down some more here. The next one. Okay, so a couple other things I wanted to point out here. This theorem, the following types of functions are continuous at every number in their domains. Now, something I want to point out here is in their domains. That's kind of the key phrase, because we may have some points that are excluded from the domain. Well, then those would also be excluded from the function being continuous at that point. Okay, so the key phrase there is in their domain. So polynomials, rational functions, root functions, trigonometric functions, yada, 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 all of those type of functions are continuous as long as we're in their domain. Okay. And then theorem 8, another way of combining continuous functions f and g to get a new continuous function is to form the composite function f of g. Okay. This fact is a consequence of the following theorem. So if f is continuous at b and limit of g of x as x approaches a equals b, then we can say the limit of f of g of x as x approaches b is f of b. I'm having a hard time reading that. So anyway, composition of functions also follows. Okay, that works. And the next slide, 23. So the one I really wanted to point out here, I'll look at both, but the intermediate value theorem is the one that I wanted to talk about. But up above, if g is continuous at a and f is continuous at g of a, then the composite function f of g, okay, is also continuous at a. So again, that kind of, it sounds like common sense because it kind of is. Now, the intermediate value theorem. Suppose that f is continuous on the closed interval a to b. Let n be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the interval a to b such that f of c equals n. Now, you're sitting there going, do what? So let me kind of show you what this means. If I have a graph and say this is my A and this is my B, and I have, I don't know, I have this f function, okay? This f function, say it starts here and it goes up here, okay? So this down here is my f of a, right? The value of the function at point A. This over here is my f of b. So f of a and f of b. What that is saying is that somewhere between a and b, somewhere in the middle here, let's call it this, there exists a c that's going to give us a value of n, okay? And n is between f of a and f of b. That's all that means. Okay, so what they're saying is in order from a function to get from a starting point to an ending point, it has to go through the points in between. That's really all the intermediate value theorem tells us. So again, we start at an A, we go to a B, there has to exist a C somewhere between A and B so that the value of the function is n. So n has to be between f of A and f of B, and C has to be between the values A and B. So this is the domain, this is the range, okay? That's kind of what they're saying. Okay, hope that was beneficial. Now, let's look at your homework, okay? Okay, your homework. This is WebAssign. Okay, I'm not going to do them all, but do a couple here and there. So first of all, number one here, from the graph of f, state each x value at which f is discontinuous. Well, you can obviously see the discontinuous parts just by looking. But here's the trick. For each x value, determine whether f is continuous from the right or from the left or neither. Enter your answers from smallest to greatest. So they want you to look on the x-axis from the left and go to the right. Okay, so first of all, this first one, x equals the smallest value. The first place that jumps out at me where f is discontinuous, if you can see that open circle there, is -4. Okay, -4. Now, is it continuous from the right or from the left or neither? Okay, now remember, in order for something to be continuous from the right, let me just write this. This would mean that f of x, as x approaches -4 from the right, that's a plus. I don't know if you all can see that. That would have to equal f of -4. Does it? Okay, so as we're traveling down this, as we're getting closer and closer from the right, does the limit of that function equal the value of the function at -4? Well, here's the trick. There is no value of the function at -4. So neither one of these are going to work. It's going to be neither. Okay, in order for it to be continuous from the left or from the right, it has to equal the value of that function at that point. And obviously it doesn't. There's a big fat hole there. Okay, so that's a neither. I hope you guys can see that. Let's go down to the next one. And it's going to be kind of hard to keep the graph up while we're looking at others, but I'll just maybe have to keep going up and down. Here, I can get the next one. Okay, so the second part, x equals what is another point of discontinuity? Well, it's got to be -2. Okay, -2 is also has a point of discontinuity. Okay, now, as I look at -2 though, is it continuous from the left or from the right? Okay, now again, remember the value of the function has to be the same as the limit from the left or the right for it to be continuous. So as I'm looking at this, this is the filled in dot. Okay, this is the open dot. This is from the right. This is from the left. Which one is it continuous at? It's continuous from the left. You all see that? Okay, continuous from the left, because as I come from the left up to this point, it equals, the value of the function equals the same thing as the limit from the left. The value of the function does not equal the same thing as the limit from the right. From the right, my limit's down here, but the value of the function's up there. Okay, so it's continuous from the left, but not from the right. Okay, I'm going to let you guys finish the next two. By the way, just kicks and grins here. Is F continuous at 0? It makes kind of this hard corner. Is it continuous? Yes. Okay, again, we didn't have to pick up our pencil. So even though it kind of makes a corner there or has a sharp angle, still continuous. Okay, so let's move on to another one. Sketch the graph of a function f that is continuous except for the stated discontinuity. So we want a continuous function except we want it discontinuous at 4. I don't really like the way these are worded. We want it discontinuous at 4, but continuous from the right at 4. Okay, notice this is just like a prepositional phrase. So it is discontinuous at 4, but even though it's discontinuous at 4, it's continuous from the right. Okay, so looks like part of mine kind of got cut off on my, that's interesting. Okay, so first of all, discontinuous at 4. This one fails right off the bat, this because it's continuous through 4. So that one's a no-go. That ain't it. Okay, don't have to worry about it. This first one is definitely discontinuous at 4. Notice the big jump. Okay, but is it continuous from the right? If I go from the right-hand side down to that point, is the value of the function at that point the same as the limit from the right? Well, from the right, I'm going to a positive number here, but from the left, the value of the function's way down here. So that ain't it. Okay, so again, we're just kind of eliminating here the possible suspects. So let's keep going. Discontinuous at 4, but continuous from the right. So discontinuous at 4. Okay, again, this one's discontinuous at 4 because we have a jump, but is it continuous from the right? So as we go from the right over, is the value of the function the same as the limit? Well, the limit value is this, but the value of the function is way up here. So again, that ain't it. So it's got to be this one, obviously. Okay, but why? Again, discontinuous. There's a big jump here at 4, but continuous from the right. So from the right side, the value of the function does equal the limit. Okay, so that's why it's continuous from the right. I hope that's helpful. Okay, let's just talk about removable discontinuity versus jump discontinuity. I'm just going to take one of the graphs and kind of show you an example here. Actually, let me go down to this one. This one down here, removable discontinuity. This is what we call removable. Okay, where literally the function goes through that point, it's just not defined. It's in algebra 2, it would have been what we call the hole in the rational function. Okay, and then we jump up and the value of the function equals something else. These are normally piecewise functions where they say, well, here's the rational function, and we're actually going to get to this in a little bit. Here's the rational function, but at this point, I know it has a point of discontinuity, so I'm going to define it as something else for that point. Okay, so that's removable. This over here, when you literally have your graph and then you have to pick up your pencil to keep drawing, this is jump discontinuity. That's what they're talking about. Okay, so they're talking about jump discontinuity at a particular point, and then removable discontinuity at a particular point. So this one has removable at 3 and jump at 1. Okay, so knowing that, you could answer that question. These two here on this one, these are both removable. Okay, we have essentially a continuous line and we just literally take 2 dots out of it and move it somewhere else. Okay, all right. Just wanted to take the time to explain the difference between removable and jump. Okay, this one. A toll charged for driving on a certain stretch of a toll road is $4, except during rush hours between 7 and 10 a.m. and between 4 and 7 p.m. when the toll is $6. Sketch a graph of t as a function of the time t measured in hours past midnight. Okay, so this first graph, obviously, that ain't going to work because we have our toll, like the cost going up. Like it's gradually, the cost of the toll is gradually going up and then it's gradually going down. And here it stays constant, then it goes up again, then it goes down again. No, that ain't it. If we look, this one over here says the cost of the toll is $6 from, I don't know, midnight to 7 a.m. And then from 7 to 10, it goes down to $4. Then from, now notice this is military time down here. They have 16 and 19. Okay, this is 4 p.m. This is 7 p.m. It's military time. So from between 10 and 4, it goes back up to 6. Between 4 and 7, it goes down to 4 and then back up. Is that what they were talking about? No, but it is just opposite. Okay, so they were talking about during the peak times, the price goes up because of course they can make more money. There's more traffic. So supply and demand, baby. So if we're talking about, these look like step functions. Anyway, this would have to be your graph here. Because again, from essentially midnight to 7 a.m., it's $4. At 7 a.m., it jumps up to $6. So between 7 and 10 a.m., when people are commuting to work, it's $6. At 10 a.m., it jumps down again. Okay. And then again, military time here. This would be 4, this would be 7, this would be midnight. Okay. So jumps up from 4 to 7 to $6, and then from 7 to midnight, it's back to $4. That would be your graph of your function. Then it says, locate the discontinuities of t. Enter your answers as a comma-separated list. If an answer does not exist, enter D&E. So first of all, locate the discontinuities. Well, the points of discontinuity are all of your intervals there. So it's going to be the 7, the 10, the 16, the 19. Okay, we can't say 24 because it cycles over again kind of on the left side there. So 7, 10, 16, and 19 would be your discontinuities. Okay, I hope you can see that. And then they ask you later on if they're jump or removable or infinite. And of course, those are jump. I'm going to let you all answer the question. Okay, so on this one, use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. Now, this goes back to our limit laws that we talked about last time. They're just breaking this apart into pieces. Okay, so remember, if we have, if it's continuous at a point, then that means the limit of the function also equals the same as the value of the function at that point. Okay, so they're saying, here's my f of x. So the limit as x approaches -1, because that was the point in question, okay, equals the limit is that all you're doing here is substituting in your f of x function. So this should just be the x plus 3x cubed. Okay, again, you're just substituting. Now, they're using the limit laws in the next part to break out, okay, the two pieces. Remember your limit laws, if you have the limit of some addition, you can say the limit of the first plus the limit of the second. So that's what they're doing here. So this is the limit of the first. This is the limit of the second. What's missing? This 3. So remember, if you have a scalar or a constant, you can pull it out in front of the limit and multiply it. Okay, so they're just splitting that limit out. Then obviously the limit of x as x approaches -1 is -1. The limit of x cubed as x approaches -1 is -1 cubed. Okay, again, you're just kind of substituting in. So then the last one, they just actually want you to do the work. So actually multiply out. These two are the same answer. Okay, I'm not going to finish it for you for the sake of time. Those two should be the same thing. So they literally just want you to poke it in a calculator and find it out. Okay. All right, moving right along. Okay, consider the following. Now we're talking about graphs. This is a piecewise function where they say, okay, we want the graph of this, and then we want the graph of this, and based on the domain, we have like two graphs kind of smushed together. Okay, so first of all, in my mind, I'm trying to think, what do these graphs look like? Well, first of all, the e to the x, if you remember, your e to the x is an exponential function. All exponential functions go through the point 0, 1. So this is an exponential function that looks kind of like that. That's e to the x. Okay, x to the fourth. Okay, it kind of, with nothing else, it's kind of a big fat parabola. Okay, we don't have any humps or anything in it. So, well, and actually I say it's fat, but that it's going to go up pretty fast. I misspoke. It's actually going to be pretty skinny. But its vertex is going to be at 0, 0. Okay. The point 1, 1 is going to be up there. So you're going to go from like 1, 1 to your next point is 2 to the fourth is 16. So it's going to shoot up really, really fast, really, well, it's going to shoot up very tall, very quickly. I'll put it that way. Okay. So we are cutting these off at 1. Okay. So if I cut these off at a 1, that's what these combination of functions are going to look like. So we want this one less than 1. Okay, so we want this piece of our e to the x, and less than 1 means that's going to be an open circle. And then the x to the fourth we want greater than or equal to 1. So at 1 it's going to be a closed circle and go up really steeply. Okay, so those are the two graphs that we're trying to push together. And then they're asking us about the limit. So what is the limit of f of x as x approaches 1 from the left? So as x approaches 1 from the left, okay, that would be this graph. From the left, what are we approaching? What's this point right here? And again, it's an open circle, but what's that point? It's got to be e to the first, right? If x is a 1, it's just got to be e. And then what's the limit of f of x if we approach it from the right? From the right, it's got to be this graph over here. From the right, we go down, and we are approaching the number 1. Okay, because that was the closed-in circle. Well, that's not why it's a limit, but that's also the closed-in circle. Okay, the one on e to the x is the open. So it says, explain why the function is discontinuous at the given number a. Now remember what it means to be continuous. The limit of the function at that point has to equal the value of the function at that point. Well, obviously that ain't true. E does not equal 1, so it's discontinuous. So since these limits are not equal, the limit of f of x as x approaches 1 does not exist, and f is therefore discontinuous at 1. Okay, so again, the limit of f of x as x approaches 1 does not exist. Why is that? Because the limit from the left is different from the limit from the right. The limit from the left is e, the limit from the right is 1. Those are not equal, so the limit at that point doesn't exist. Okay, I'll let you guys finish that one. Okay, this one, how would you remove the discontinuity of f? In other words, how would you define f of 3 in order to make f continuous at 3? Well, here's the deal. We have to simplify the rational function that they have there. Well, what do you mean simplify? I mean, just like I would ask you to simplify fractions, we need to factor and cancel what we can't. So in other words, up here, this f of x. This top part can be factored. It would be x minus 3 and x plus 2. And then we've got the x minus 3 on the bottom here. So now we can actually cancel those two. Okay, so all that's left is x plus 2. Well, what's the limit, or what is f of 3 when we've redefined f of x as x plus 2? Well, that's got to be 3 plus 2 or 5. Okay, so first you have to simplify the rational expression. Okay, now this is why, let's go back and think for a minute again. I'm a visual person of the graph. If I graphed that f of x, it would be a nice smooth curved line, except for at the point 3, it would have a hole. Not a vertical asymptote, it would have a hole. Because if I was able to cancel that out, what I'm really graphing there is the x plus 2, but I've got a hole at the point 3 because I couldn't get started on the math with a 3 in the denominator because it would make it go to 0. Does that make sense? Okay. Now, next one, explain using the theorems why the function is continuous at every number in its domain. Continuous at every number in its domain. First of all, this is a rational function. Okay, again, root word of rational is ratio. Anytime you've got a ratio of polynomials, it's a rational function. And why is it continuous at every number? Well, the first thing that jumps out at me is when I look at this, look at the denominator. Is there any value of x that's going to make that equal 0? Nope. Okay, because nothing squared is ever going to give you a -9. And that's the only thing that would make it equal 0. Now, if it were x squared minus 9 on the bottom, then we'd have some points of discontinuity. Okay, but this, it's just a rational function, so it is continuous at every number in its domain. Okay, and remember, the key word there is in its domain. If that had been x squared minus 9 on the bottom, we would have had to exclude -3 and 3 from its domain. It would still be a nice continuous function other than at those 2 points. Okay. Okay. Moving right along. Locate the discontinuities of the function. Okay, well, it says illustrate the discontinuities by graphing. A graphing calculator is recommended. Well, that's great, good, and fine. Honestly, though, if you're going to show the discontinuities, you actually need to kind of do the graphing first. So I actually did this in Desmos. I just wanted to show you guys. That's the one. So I graphed this in Desmos so you could tell which one it was. What's the point of discontinuity? 0. Now, one thing I wanted to point out in Desmos, that point right there is filled in. That's 0, 0. This point up here, okay, not. This one is the one that's shadowed. So 0, 0. Okay. So our point of discontinuity would just be 0. And then, of course, from the graph, you could tell which one it was. Desmos is our friend. Let's move along. Now, use continuity to evaluate the limit. You guys, all you really have to do on number 10 is plug a 1 in and solve it. Okay, that's it. Just plug a 1 in because the limit of x, the limit of that function as x approaches 1 is defined. Just plug the 1 in and solve it. Now, number 11. Again, piecewise function. So find the x value at which f is discontinuous and determine whether f is continuous from the right or from the left or neither. Okay, you're going to have to do some graphing here. Again, just want to point out that you've got 3 different graphs. So the graph of 4 plus x squared, remember, is just your parabola, but it's shifted up 4. Okay? The graph of 5 minus x, again, is just a line that the y-intercept is 5 and the slope is a -1. So it's going to look like this. Okay, that's the line. Okay, x minus 5 squared is a parabola that shifted right 5. Okay, so parabola that shifted right 5. Now you have to look at the domains and figure out what part of these graphs we're using. So this first one, x is less than or equal to 0. So that's a filled in, and we're looking at the left-hand side of it. This one is between 0 and 5. So here, it's open at 0, it's filled in at 5. We're just using this piece of it. Okay? Over here, it's greater than 5, so this would be an open circle on 5 going up. Combine all 3 of those together onto one graph, and you got yourself an answer, and then you have to figure out where it's continuous from. What is its point of discontinuity? When do you actually have to pick up your pencil? That's the point of discontinuity. Okay? And then if that's the point of discontinuity, is it still at that point continuous from the right or the left or neither? Okay, I'll let you all play with that. Almost done, guys. I know this is kind of long, but I didn't want to split it up into 2. Wanted to be done. Okay, which of the following functions has a removable discontinuity at A? If the discontinuity is removable, find a function g that agrees with f for x not equal to a and is continuous at a. Here's essentially what we're doing. We are simplifying these rational functions. We are taking out the part that would give us the whole when we graph it. That's like the one I was talking about earlier. If we graphed it, you know, after we canceled out the x minus 3 or whatever, I forget what problem number it was, then we'd have the graph of a nice straight line. But the way it was written as a rational function with the x minus 3 in the denominator gave us a point of discontinuity at 3. So what do I need to do? How can I rewrite it as a new function, but without any discontinuity points? Well, simplify it. Okay, so for instance, on part A, I'm not going to do all of these, but I will do part A here. X to the 4th minus 1 over x minus 1. I need to simplify. Believe it or not, that top is the difference of 2 squares. Okay, so this is x squared minus 1 times x squared plus 1 all over x minus 1. Still not done. Okay, this right here is still the difference of 2 squares. Okay, so we've got the difference of 2 squares inside the difference of 2 squares. Then we still have the x squared plus 1, and of course that's still over x minus 1. Okay, so the x to the 4th minus 1 was difference of 2 squares, and then half of that was still difference of 2 squares. Now I've got these x minus 1s that'll cancel. So that leaves me with the function x minus 1 times x squared plus 1. That's my g of x. Now, I don't know if WebAssign will take it that way or if you need to multiply it out. If we multiply it out, this is obviously what? X cubed minus x squared. Nope. X cubed plus x. Oh, sorry, that's a plus. That's why. Plus x squared plus x plus 1. Okay, that would be my g of h. That's what we're talking about. That's what your g of h would be. You have to simplify your rational functions. okay? And then it asks you if the discontinuity is removable or not removable, okay? Anytime you have this part that's in the denominator, okay, that's what creates a hole. That's going to be removable, okay? So this one would definitely, the discontinuity is removable. That's where you literally, the function is a nice, consistent curved line, except for at that point. Okay. Now, actually, I think I want to show you. I think I did another Desmos on that. Aha, I did. Okay, so the x to the fourth minus 1, that is the green line. Okay, now notice what happens as x approaches 1. Look at my finger. Oh, where'd it go? Right there. Do you see that? 1 comma undefined. They don't actually put, my finger's kind of on it right now. You can't see it, but there's actually like a hole. There's an open circle there on 1 comma undefined. However, if, let me get rid of this one. If I do another graph, okay, I can do what I just did for my g of x. So let's do y equals x squared, whoops, x squared. It's not liking me. And actually it was x cubed, wasn't it? So I want x, oh my goodness, it's still in the, there we go. X cubed, okay, move it over, plus x squared. Now look at this up here, look at this black line as opposed to the green line, okay? Look how this one's changing as opposed to this was our original. Look at how they're changing, okay, as I add different pieces to it. Plus x, okay, plus 1. Oh, what just happened? The black line got put on top of the green line because we reduced, we simplified that rational function. We canceled out that x minus 1. Okay, so now look what happens at the point 1. Do I have an undefined? Whoop, I can't hardly get to it. No, it's 1 comma 4. My board is shaking because the air conditioner kicked on. So it is defined now at that point where the green line up above wasn't. Okay, that's what we're talking about. The last one I want to go over is the intermediate value theorem one. And then we'll be done, I promise. So intermediate value theorem, whoa. Remember the intermediate value theorem just says there's a point C between my begin and end points in my domain such that there's a value of the function between the begin and end points of the range. Okay, that's essentially what it says. So use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So we know that this would be continuous, okay? On the closed interval 1, 2, f of 1 equals plug in whatever that is. You can poke it in your calculator. And f of 2 equals plug in whatever that is. Now, obviously, and they kind of give you the answers there. Since negative 2 is something less than 14, I can't see that because of my, anyway, I'll let you guys fill that in. What that's talking about is it has to cross the x-axis somewhere between that. Since we have a negative on the left-hand side and we have a positive on the right-hand side, that means at some point it had to cross the x-axis in that interval to get from below the x-axis to above the x-axis. That's the intermediate value theorem. Okay, I will let you guys go. That finishes your section 2.5. Okay, due at the end of the week.